All right, welcome everybody. Today we're going to talk about lesson number 56, and this is day one of section 5.2, which is all about verifying trig identities. Now, what we're going to be doing here in section 5.2 is actually very similar to what you did the first day in section 5.1. Using your formula sheet and using a series of algebraic maneuvers, your goal is to rewrite some trig expression into a different trig expression. The one main difference is that you're actually going to now know what the answer is supposed to be, which should hopefully make it a little bit easier for you to determine the path that you should take to get from one side to the others. So let's kind of keep the goal in mind here. The goal of all these problems here in section 5.2 is to use the fundamental trig identities, which again is your formula sheet, and to use the rules of algebra. So factoring, reducing, common denominators, all the stuff that we did back in the first day of section 5.1, we're going to use that combined with our formulas in order to rewrite trig expressions. When you're trying to figure out what side to start with, generally speaking, if you choose the addition and subtraction side, it is usually an easier path than choosing the side with multiplication and division. I say generally because not always. The more you do of these, the more adept you'll get at deciding which side should you pick. But generally speaking, using addition and subtraction, that side will give you a little bit of a better idea of how to get started, where sometimes it's a little bit harder to start with the multiplication and division. So as you go ahead and try to accomplish your goal, here are a series of steps and some tips that you might want to consider. So bullet number one here, practice makes perfect. The only way to get really, really good at these is to do them. Not just to watch me do them, not just to copy the answer key or watch a friend do them, but you actually have to do them yourself in order to get the practice. Secondly, you're only allowed to work one side at a time. Every problem is going to have an equal sign, so you're going to think of it as a left side and a right side. You're only allowed to work one side at a time. Keeping that in mind, you cannot move across the equal sign. You cannot cross multiply. You cannot divide to both sides. You can't add to both sides. You can't square both sides. What you're trying to do in these problems is you're trying to prove that they're equal. In order to prove that they're equal, you cannot assume that they're equal. So it's not an equation. You're not allowed to do something to both sides. Then bullet 3 here, choose the more complicated side to work with first. If you choose the more complicated side, there'll be more things for you to rewrite using the identities, and there'll be more operations for you to do algebraically. And again, generally speaking, that's the addition and the subtraction side. All those strategies from the first day of 5.1, the conjugate, the common denominators, the factoring, those are all things that you should be using as you approach these problems. Then be sure that you're copying the problem accurately. You would probably be surprised in years past how many people come up to me and say, I cannot get these two things to be equal. And the truth is it's because they're not, because they've copied the problem incorrectly. And finally, you have to do something. These problems are not going to prove themselves. So the only way for you to even have a shot at getting the right answer is to go ahead and do something to go ahead and get started. So take a look here at the directions, depending on what section of the book we're in, or depending on, where you see these problems, you might see prove the identities. You might see the word show that they're equal, or you might see the word verify that they're equal. They all really mean the same thing. It means go through a series of steps to prove that the left side is in fact equal to the right side. Now, just so you know, there are problems out there that I could give you where they're not equal. I'm not going to do that. I promise I'm only going to give you ones that are true. But just so you know, for future reference, it is possible out there that somebody could be trying to trick you. So again, take a look at the left side, secant squared minus 1 over secant squared, and then the right side, which is sine squared. Again, just to be clear, you cannot do anything across that equal sign. You are trying to prove or show or verify that they're equal. So you cannot assume that they are equal. If my message to you is to start with the more complicated side first, I'm sure you would agree that the secant squared side, there's much, much more to be done. So we're going to go ahead and start there. So using my left-hand side, I have a numerator and I have a denominator. And look at what your final answer is. Your final answer is just a nice simple sine squared. In order for some big messy fraction on the left side to reduce down to be a nice simple sine squared, that means that some things are going to have to cancel. So the first thing I notice is secant squared minus 1. When I see the squared and when I see the 1, that's a clue that I might want to look at my identities. If I look at my Pythagorean, if I go ahead and subtract the 1 to the right-hand side, secant squared minus 1, that is going to be equal to a tangent squared. So I'm going to go ahead and start by replacing the numerator with a tangent squared of theta. And I'm going to go ahead and leave the secant squared of theta just for a second. Then, again, if you're trying to get things to cancel out even farther, you would want to try to find some kind of commonality that a tangent and a secant has, and hopefully it would be clear to you that you should be using sines and cosines. So again, flip back to your formula sheet as much as you need to, but the goal hopefully is that the more you do of these, the more you can kind of just do them from memory. So a tangent is of course a sine over a cosine, which means a tangent squared is a sine squared over a cosine squared. And again, I'm going to kind of be mixing the variables just to give you the practice, but if you really want to make everything x, you can. So that's just the numerator, sine squared over cosine squared. Then the denominator, I'm going to do 1 over cosine squared. When you're doing these problems, generally speaking, it gets worse before it gets better. So now you have a complex fractions inside of fractions. But usually when that happens, the next step is kind of the money step. Remember, how do you get rid of complex fractions? You do the keep, change, flip. So you're going to go ahead and do sine squared over cosine squared. That's the numerator. Change the big division to a multiplication. Cosine squared theta over 1. Well, would you look at that? You can cancel out those cosine squared theta, and you're going to go ahead and just be left with sine squared theta. So in order to be done here, in order to kind of make sure you know that you're done, you have to do something. So sometimes I personally kind of just like to box my answer. I put those 2 lines there just to show that I'm done. Some people like to just say, okay, I know I have the left side, it's equal to the right side, and then they do a check mark or a smiley face, just something to indicate that you are in fact done. And again, you will be done when your left-hand side is now completely and utterly identical to your right-hand side. So again, shouldn't seem all that different than what we did back in section 5.1, but maybe the fact that you know what the answer should be makes it a little bit clearer, the steps that you should take to get there. Let's go ahead and try another one. So 1 over 1 minus cosine of beta plus 1 over 1 plus cosine of beta equals 2 cosecant squared beta. So again, if you're trying to decide left side or right side, choose the side that is more complicated, which I think hopefully you would agree is in fact the left-hand side. Keep in mind, what is the problem asking you to do? The problem is asking you to add fractions. So how do you add fractions? Well, you're going to go ahead and find a common denominator. So the common denominator of 1 plus the cosine of beta and 1 minus the cosine of beta is just those 2 things multiplied times each other. And then in order to have that common denominator, you are going to take this fraction on the left and you have to multiply it by 1 plus cosine of beta over 1 plus cosine of beta. So this 1 plus cosine of beta is going to be multiplied times the 1, which is how you're going to get 1 plus cosine of beta. And again, that's just dealing with the first fraction. Then take a look over here at the second fraction. In order to find a common denominator, you would have to multiply both of those by 1 minus cosine of beta. So this 1 on the top, you're going to multiply by 1 plus cosine of beta. And again, I pointed it out a couple of times here, but be careful. Here you have an addition between those 2 terms. Sorry, that should be a minus. Here you have an addition between those 2 terms. If it was a subtraction, you would have to very, very carefully distribute that minus. So just be cautious. So now if you take a look at the top, some good things happen. The good thing being that the positive cosine and the negative cosine cancel. 1 plus 1 is a 2, which that's looking really good because we need one of those. Then in the denominator, remember my tips in the past, if you have a common denominator that is a pair of conjugates or the difference of squares, then 99.9% of the time you are going to want to multiply those out. So if you multiply that pair of conjugates, it's first and last, which would be 1 minus cosine squared of beta. Again, always keep in mind what it is you're trying to get equal to. So I have the 2. I'm trying to get a cosecant squared. A cosecant squared is the reciprocal of a sine. So how can I possibly get a sine in here? Well, 1 minus cosine squared, if I go back to my formula sheet, that is simply equal to sine squared. And then I'm almost home. Just a slight algebraic maneuver. I'm going to separate the 2, and then I'm going to write 1 over sine squared. And again, you're just allowed to separate that multiplication so long as if you multiplied it out, you go back to the original. So the 2 remains a 2. The 1 over sine is a cosecant. So the 1 over sine squared is a cosecant squared. And would you look at that? Game over. Do something to let me know that you're done. And then because you're done, that means that the 2 sides, the left side and the right side, should be perfectly equal. Just so you know, for some reason, the way that these problems are designed, it almost always winds up being the left side that you work on as opposed to the right side. Again, not always, but a lot of the time. So I'm not really even sure why that is, but it does happen. So something to keep in mind. Let's go ahead and try a few more. So here in number 3, you're trying to prove that the cosecant minus the sine is equal to the cosine times the cotangent. And just to be clear, this is true. So if you were to pick an x like pi over 6 or 45 degrees, and you were to calculate the cosecant of that angle, and you were to subtract the sine of that angle, it will absolutely be equal to the cosine of that angle times the cotangent. That's the whole point. So when deciding which side to work on, again, generally speaking, addition and subtraction gives you a little bit more to do. So we're going to go ahead and again do a left side. I see a cosecant and I see a sine. I see no squares. So how can I kind of get those two speaking the same language? Well, they're both going to speak the language of sines. So I'm going to rewrite the cosecant as 1 over sine minus sine over 1. Follow the algebra. The algebra is telling you to subtract. So how do you subtract fractions? Common denominator. And again, the common denominator of 1 and sine is sine. Because this 1 over sine already has the common denominator, then your numerator is just going to remain a 1. Then it's a minus. Over here, you're going to have to multiply by sine over sine. So this sine is going to become a sine squared. Once you see that 1 and once you see that sine squared, you should think to yourself, formula sheet. If you look at your formula sheet and you move 1 minus sine squared to the right, that's going to be equal to cosine squared. So I'm going to go ahead and replace my numerator with a cosine squared. And then believe it or not, if you find yourself doing these problems and you feel like you're stuck, you look at your left side and you say to yourself, how is it possible that it's equal to the right side? 8 times out of 10, it means that you're done. You just have to rewrite it so that you know you're done. So you would like there to be a cosine out front. So why don't I go ahead and put one of the cosines out front? If I put a cosine out front, I'm left with a cosine over a sine, which I'm going to go ahead and put next door. And again, if I was to multiply that back out, it would absolutely go back to the green step. That's why I'm allowed to do that. And then if you look at that, you have a cosine. You have a cosine over a sine, which is a cotangent, which means game over and you are done. Generally speaking, you should really kind of do all these steps down one side of the column, the left side or the right side. I'm kind of, doing a little bit differently just so you can see everything on the same screen. But again, once you get the two things equal, that's really the whole goal here. Number 4, so cosecant to the 4th times the cotangent equals that right-hand side. So you have a lot of things going on here. Not only do you have square terms, which a lot of the times implies the Pythagorean terms, but you also have higher powers to the 3rd and to the 4th. So you kind of want to keep that in mind. So which side should you go with here? It actually wouldn't matter. They're both kind of equally difficult or equally easy, however you want to look at it. I'm going to actually go left side here because I want to show you, again, just some techniques that you might not normally think of. So as I mentioned a few minutes ago, cosecant to the 4th, there are no formulas that are cosecant to the 4th. There are, however, formulas that are cosecant squared. So I'm going to go ahead and take that cosecant to the 4th, and I'm going to rewrite it as a cosecant squared times a cosecant squared. Again, maybe you wouldn't think to do that, but you absolutely can. Any algebraic maneuver that is legal is possible. And again, the whole point of doing more and more of these is that you hopefully start getting a feel for what needs to be done. So from here, if you take a look and you look at what you have and you look at what you're heading towards, notice that there's an addition sign over here on the right. We don't have any addition signs to speak of right now. So we're going to go ahead and try to add one in. So I'm going to go ahead and replace one of my cosecant squared into something that has an addition sign. So going back to my formula sheet, if I go ahead and look at the cosecant squared, that is equal to 1 plus cotangent squared. So I'm going to go ahead and replace that second cosecant squared with a 1 plus cotangent squared. So now from here, okay, take a look at what you have, take a look at what you're heading towards. What do you have done that is correct? Well, you have the cosecant squared, and then you have a cosecant squared, so that's good. Then if you look at what it is you're trying to get, well, you're almost completely there. All you have to do is distribute. So go ahead and do that distribution, cosecant squared of x. You're basically distributing backwards, so 1 times the cotangent, plus a cotangent squared times a cotangent, of course, gives you a cotangent cubed. And again, that is exactly what you were trying to get, cosecant squared times the cotangent plus the cotangent cubed. Just FYI, had you started on the right side, it actually would be this exact same proof in reverse. It would be the exact same number of steps, and it would be equal in difficulty, but perfectly acceptable that you could do that. Again, you technically can also work both sides, but you can just only work one side at a time. So if you find yourself getting as far as you possibly can on the left side, and then you stop, you can go back and do things to the right side. You just have to work just one side at a time, and you're not allowed to go across the equals. All right, a couple problems to go here. On the left side, we have the cosecant of negative x divided by the secant of negative x equals the negative cotangent of x. Now, when you see something inside of the function, like a negative or a pi over 2, I know those can look a little scary, but the truth is those are sometimes the easiest proofs to do because there are only a handful of formulas that you can replace them with. Before I go ahead and actually use that negative inside, I'm going to go ahead and start by rewriting the left side. And again, as the more complicated side, the fraction on the left tends to give us more to do than just the single fraction or the single term on the right. So I'm going to rewrite the cosecant of negative x as 1 over the sine of negative x. And then again, a big fraction bar. And then the secant of negative x is 1 over the cosine of negative x. Then I'm going to go ahead and look at my formula sheet and replace each of these even and odd functions with something else based on their identities. So if I go back to my formula sheet, the sine of negative x, that is equal to negative sine of x. And then the cosine of negative x is going to remain positive. Again, these are your even and odd identities. So as I go back here and I go to make my replacement, so 1 over the sine of negative x, that's really going to be 1 over the negative goes on the outside because sine is an odd function. Still a complex fraction, so big fraction bar. 1 over, and then this goes back to a positive because that's an even function. So from here, again, whenever you have a complex fraction, you're going to go ahead and do the keep, change, flip. So 1 over negative sine, change the big division to a multiplication, cosine over 1. Nothing cancels, but a cosine over a sine is a cotangent. And then whether the negative is on the top or the bottom, it doesn't matter. You can go ahead and put it out front, which means you now have the negative cotangent is equal to the negative cotangent, which is exactly what you're looking for. So you're going to get a variety of problems, some short ones, some medium ones, some longer ones. It really is just a matter of mixing and matching. Sorry. And then again, also as a reminder, there's more than one way that you could have done this. Maybe you would have used the actual identities for the cosecant of negative x and the secant of negative x, and then rewritten it as sine and cosine after. That would have worked equally well, and you still would have gotten to the correct answer. Again, starting over on the right-hand side and trying to make it into the left-hand side, it is possible, but it would be a lot more difficult. So again, always try to start with the more complicated side first. Final problem of the day, and the truth is that this is the longest one, and no matter which side you started on, you would have to use the conjugate strategy, which not that the conjugate strategy is a hard one, but it is just sometimes one that you are the least likely to think about. So in this case here, I'm actually going to go ahead and start with the right side because there's a strategy in particular that I want to go ahead and show you. So over here on the right-hand side, you have the cosine over 1 minus sine, and then on the left, you have the secant plus the tangent. So again, I know that I told you that generally speaking, it was easier to do addition and subtraction as opposed to multiplication and division. So there are exceptions to that rule. And again, because I know what this proof is supposed to look like, and because I know what it is I want you to do, we're going to go ahead and go right side. So if we're going on the right side, notice we have the cosine and the sine. There aren't any squares. There's nothing that I can easily rewrite the cosine and the sine as. So I'm going to go ahead and bust out the conjugate maneuver. The conjugate is going to be the conjugate of 1 minus sine of y. Remember, the conjugate is the same front, the opposite middle, and then the same back. You're going to have to do one on the top and one on the bottom. Again, just to reiterate, why is it plus? It's because it has to be the opposite. Why do you need one on the top and one on the bottom? Because then you're really just multiplying by 1, which is perfectly legal. When it comes to multiplying in the numerator, you're multiplying a cosine times a 1 plus sine. Because you don't know if it's going to be helpful to multiply those or not, you're not going to. Whereas in the denominator, that's the difference of squares. And remember, 99.9% of the time, you are going to want to go ahead and multiply those. So looking at what I have here doesn't really seem like it's much easier than what I had so far. But if I take a look at the denominator, 1 minus sine squared, I can go ahead and make that slightly simpler if I replace it with a cosine squared. So that's going to give me a cosine and a 1 plus sine in the numerator, and then a cosine squared y in the denominator. Because of the fact that the numerator is something times something, you're allowed to go ahead and reduce this cosine with one of these cosines, which means that's going to leave you with 1 plus sine over cosine. And then from here, you're going to have to use the heart strategy, or what I sometimes call it is the break it up strategy. Whenever you want to go from one big term into two, you're going to go ahead and put the first value of the numerator, 1 over cosine, plus sine over cosine. And again, as long as whatever algebraic maneuver you do could be undone in the correct way to go back a step, that's how you know that it's legal. 1 over cosine, well, would you look at that? That is equal to a secant. A sine over a cosine is equal to a tangent. And because that is exactly what the left-hand side was equal to, we know that we are completed. And just to let you know, had you done this problem from the left side, you would still have to use the conjugate. But again, it would be the exact problem in reverse. So you absolutely could do that. Just to point out, you would start by rewriting secant plus tangent as two separate fractions. You would then put them together with a common denominator, and then you would have had to multiply in this step by the conjugate, because that's the only way that you could possibly get back to the beginning. So again, there's definitely more than one way to do these problems, and the more you do of these, the better you'll get at finding the most efficient way. So here in day one, I was just showing you a bunch of different strategies. And again, the fact that you actually know what it's equal to. So here is homework number 56. For the last two problems, it gives you several directions, but you're just going to prove them like the rest. So again, within this set of problems, there are some easy ones, some medium ones, some hard ones. So we're going to work on these next time I see you in class. So thanks very much for tuning in, guys, and we will catch you next time.